Oof. Continuity. Last day of notes. By the way, some of you noted that it says AP Calculus BC. BC just covers more than AB. So the introductory calculus stuff, the whole first semester of BC Calculus is also in AB. So you'll notice this next year sometimes too. Sometimes I don't take the time to change the notes from BC to AB. It's the same stuff. BC just does it faster so they can get to more stuff. And then now that we're past pre-cal and into calculus, it feels like we're doing calculus BC stuff. And I mean, I guess we kind of are, but this is like day one of calculus BC stuff. Continuity. Continuity is sometimes easy and sometimes hard. And conceptually, like, it's super easy. Like, you can look at a graph and know if it's continuous because your brain just has a feel for what it means to be continuous. In fact, let's just you can draw a graph without lifting your pencil. You can draw the graph without lifting your pencil. So no holes, no jumps, no asymptotes, nothing crazy. So it's pretty easy to spot a discontinuity. But technically, it kind of has a tricky definition, like a math definition. So continuity, when people ask, is it easy or hard? It's like, well, both. Like just looking at a picture, sure, it's easy to see if it's continuous or not. But then if I ask you to prove its continuity or discuss its continuity or talk about the different types of continuity, there are some very technical issues going on. So if I don't know, just know that ahead of time. But it's a huge deal in calculus, primarily because 2 or 3 of the most important ideas depend on continuity. Like if something's not continuous, you can't use this idea. And so most of the things are continuous so that you can use the calculus things, but you have to show that it's continuous. So it's this basic foundational thing, but if it's not there, it kind of blows the rest of it up. So it's super important because it matters to definitions, theorems, derivatives. So it is a very big deal in calculus. Let's look visually. This should be the easy part, the part that you're like, yep, that's continuous, and nope, that's not. So your picture doesn't have to look even really very close to mine. Some polynomial looking thing there. What do you think? Is that continuous? Yeah. Let's just so we can call it something. Let's call it f of x, and we'll say f of x is continuous for all x. That for all x is another part that makes it sometimes tricky, because sometimes a graph is continuous everywhere except, and the exceptions are important. Next picture has a little hole in it. Continuous? No. Well, be careful how you phrase it. Let's say g of x has a point discontinuity. Point discontinuity at x equals, I guess we just call that point A, at x equals A. Point discontinuity. That's a fancy word for what? What's that look like? Use a word that we've already used a bunch of times. A hole. So you already know what a point discontinuity is and what creates it and lots of stuff about it with limits and all that. We just hadn't called it a point discontinuity until now. And this is what we call, this is a removable discontinuity. Removable discontinuity. Removable just means you can fix it pretty easily, right? Like fill in the hole and it's now continuous. Or if you think about the equation, you remember what kind of equation leads to a hole? Or what about the equation leads to a hole? What's going on in an equation that leads to a hole? Yeah, factors that cancel. So if you canceled the factors and pretended they were never there, then you would have removed the hole. So we like holes because they're easy to fix. They're a removable discontinuity. And we also need to say that g of x is continuous everywhere else. So is g of x continuous? No. But more specifically, it's not continuous at A. Everywhere else, it is continuous. And sometimes that matters, because if you want to use one of those calculus definitions or concepts when you're not at A, then it's fine, it'll work. But it wouldn't work at A. So point discontinuity at x equals A. Point discontinuity is the same thing as a hole, which is also a removable discontinuity. So a lot of today is some new terms put on things you already know. Speaking of new terms on things you already know, what's coming next on this picture? A vertical asymptote. So let's call that h of x. It's got a vertical asymptote at A. H of x has an, you want to guess what name we put on this kind of discontinuity? This one was a point discontinuity. Happens at point. This one is not a bad guess. Where are these things going to? This is called an infinite discontinuity. So again, you've seen that graph before, you've seen the picture before. You would have known it's not continuous, but now we've got a special name for it. That's an infinite discontinuity at x equals A. And infinite discontinuity is the same thing as a vertical asymptote. And then lastly, can you guess what other type of discontinuity there is? You've seen it before. It happens on piecewise sometimes. Right, that thing's not continuous. Let's call that picture J of x. And we'll say J of x has a, any guesses on what kind of discontinuity we would call that? What's the graph doing at A? How would you what kind of language would you use to say what's happening at A? That's it. It has a jump discontinuity. At x equals A. the fancy way to say that is that the limit from the left is not equal to the limit from the right. So there's our sort of connection with limits. So you've seen all of those, and you could probably have told me ahead of time, probably even 3 years ago, what's continuous and what's not. But now we got some fancy names for them. We also have a couple of categories here. This first one, we said this already, is a removable discontinuity. Because you can fix it. Like you can remove the hole and it doesn't really change the shape of the picture. The second two are non-removable discontinuities. Because you can't fix them. Like there's no way to remove the right. You can't fix them without changing more than one point. Right? There's no way to fix a vertical asymptote. There's no way to fix. Well, I mean, I guess you could sort of connect those, but then that would be a different function. So removable is a hole, is a point discontinuity. All of those are interchangeable. Non-removable are the discontinuities you can't fix, asymptotes and jumps. So again, most of this stuff makes sense. We've just put some new words on it to give us a better vocabulary to talk about. All right, this next section, talk with your partner to write your own definition. Like you're not going to come up with the technical definition of continuity, at least I don't think. F of x is continuous at x equals a if and only if, oh, there's another geometry flashback, right? The if and only if definition. The limit as x approaches a from the left equals the limit as x approaches a from the right. Let's pause there for a minute. Limit from the left equals limit from the right. Would that be enough to establish continuity? Maybe look at your pictures. Does one of those pictures have a limit where, and we could just pick A on this one if we wanted to see a continuity one. Does one of those pictures have a spot where the limit from the left equals the limit from the right, but it's not continuous?
Point discontinuity?
Yeah, point discontinuity. So that just establishes that they go to the same spot. But next we need to fill in the spot. Like that might mean there's a hole. What would establish that there's not a hole there is if the function is actually there. So the limits need to match, so not a jump, but there also needs to be a point inside the hole and not a hole there. All right, that's kind of a big deal. That's the definition of continuity that we'll use in calculus. And even on the AP calculus test, there could be a question, a free response question even, that says, discuss the continuity at x equals a for this function. And what they would be looking for is the limit from the left equals the limit from the right equals the function value. If a function is not continuous at x equals a, we say the function has a discontinuity at x equals a. I said that already. Two kinds of discontinuity, removable and non-removable. Again, removable is the holes. And that would be if the limit as x approaches a from the left equals the limit as x approaches a from the right, but then that's not equal to the function at a. Right, that would be a hole. Non-removable, that's the vertical asymptote or jump. And that would be where x approaches a from the left does not equal the limit as x approaches a from the right. So sort of looking at the different breakdowns in the definition. If the two limits are equal, well then you might have a hole, but you got to fill in the hole to make sure it's continuous. The ones you can't even fix are if the limit from the left and the right aren't even the same, then there's no hope of fixing that. Questions? Okay, so let's see how to use this, or what to look for. Oh, speaking of what to look for, we've kind of already answered what we're looking for on number 1. State the values of x, if any, at which the function has a discontinuity. So what do you think on number 1a there? Where is it not continuous?
-2.
Not continuous at x equals -2. I guess that completes the question. Usually we would ask for more than that. So that's it. What's going on at x equals -2? There's a hole there. So the question didn't really ask that yet, but anything that makes the bottom 0 is going to be a problem for continuity, because if it makes the bottom 0, this goes back to last semester pre-cal, it's either a vertical asymptote or a hole. All right, part B, what are we concerned with on this question?
Jumps.
A jump, right? So, like, let's talk about branch A and branch B. Branch A and B are continuous, right? Because that's one's a parabola, one's a line. Not worried about that. But x equals 1 might be a jump. Might be a jump. Like maybe they rigged it so it's not a jump. So how do I test to see if it's a jump or not? Any idea on how we figure out if there's a jump? Here's your hint. If there's a jump at x equals 1, plug it in. Plug it in where?
The equation, x² + 3 divided x - 7.
Yeah, plug it into both. Now, you have to be careful saying that, because the function itself would only be on branch A, right, because of the equal sign. But we're thinking about limits and like coming from the left, coming from the right. We want to plug in something really close to 1 into branch B. So for part A, 1² + 3 = 4. For branch B, 5 times 1 - 7 would be -2. They don't match, so there's a jump there. The very technical, okay, so again, the concept versus technical. So concept, yeah, there's a jump there. X equals 1, on branch A is 1, on branch B is something else, so that they don't match. The technical way to say that is, as x approaches 1 from the left, is not the same thing as the limit as x approaches 1 from the right. So there's a discontinuity at x equals 1. And we need to say at x equals 1 because there's not a discontinuity anywhere else. Everywhere else it's fine, but at 1 we're worried. Or not we're worried, there's a jump there. All right, on number 2, let's change this function to be x² + 3 when x is greater than or equal to 1, and 5x minus 1 when x is less than 1. And you can probably guess why I did that and what that's going to make happen. So again, we have a potential jump at x equals 1. Maybe. That's where the function changes from one branch to the other. But we need to check and see, because maybe they magically tied them together where there's not a jump. So on branch A, 1 squared plus 3 is 4. On branch B, 5 times 1 minus 1 is 4. So no jump, which means this is continuous for all x. So there's our conclusion. The answer is it's continuous everywhere. But we had to check x equals 1 because we thought maybe there was a jump there. If we graph this on the calculator, let's see, 5x minus 7 does that. And then x squared plus 3 is some sort of parabola looking thing. So it's still two different pieces, but they sort of rigged it so that they would connect, and there's no jump. Question 3 is, I don't know if it's on every AP calculus exam, but it's on most of them. Find the value of k that makes g of x continuous. Oh, so find k that would make this continuous. So what value are we concerned with? Where might the jump be? 1, because that's where we're changing from branch A to branch B. So we need to look carefully at what's going on at x equals 1. So if we plug in 1 to branch A, 1 squared plus 3 is 4. Okay. If we plug it into branch B, I don't know what k is, but I get k minus 7. Well, what do I want to be true at x equals 1? What needs to be true for this to be continuous? These two pieces need to equal each other. So 4 needs to equal k minus 7 so that they match. So if k equals 11, then branch A equals branch B at x equals 1. And that would force them to be matched up rather than having a jump there. Super common question. You'll see it again on the homework, on the review, on the test, probably on the AP test. Number 4, which of the following is continuous at x equals 1? Okay, so more of the same stuff here. Okay, choice 1. Well, something's going on at x equals 1, because I've got x minus 1 in the denominator. But let's factor this and see what's happening. Okay, so a little more specifically, what do we think is happening at x equals 1? A whole, because we canceled the x minus 1. I put whole question mark because there's more to this. Maybe this second spot down here, maybe that fills the hole in. So let's see, at x equals 1, there's a hole at, how do I figure out the y value of the hole? How do I figure out the y value of a hole? After I cancel out what makes the hole, what do I do with x equals 1? plug it back in. So 1 minus 1 equals 0. So there's a hole at y equals 0. Okay, but now I need to check and see what this says. That says if x is 1, y is 1. So my dot's right there. So let's make sure we answer the right question here. Which of the following is continuous at x equals 1? So is that continuous, yes or no? No, there's a hole there, and it was not filled in. All right, number 2, I can't factor, so something's going on at what value are we worried about here? At x equals -1, there's a vertical asymptote. Everything else is fine, but the question was at x equals 1. So this one's a yes. Yes, it's continuous at x equals 1. It's not continuous at -1, but we don't care about -1. Discontinuous at x equals -1, continuous everywhere else. So sometimes we have to be very careful when we say, is that graph continuous? Is the graph continuous? No, but the problem is only at -1. So if we say, is it continuous at x equals 1? Yes, it's fine there. And then lastly, it looks like we have a potential jump. So let's plug in 1 and see what happens. 1's everywhere. Half of 2 is 1. 1 plus 1 is 2. Oh, for branch B, there's nothing to plug in. The answer is just 2. So yes, that's continuous at x equals 1. Continuous everywhere else as well. So 2 and 3 are continuous. Number 1 had the hole in it. Oh, another K problem. Ooh, with fractions even. So how do I figure out what K is? Or how do I make sure there's not a... Yep, plug it in to branch A, plug it into branch B, set them equal to each other, and then figure out what K is. So K times 1/8 minus K times 1/2 minus 1/4 equals, so all of that was branch A. Branch B, 32 times 1/4 minus 2. Fractions. Let's see, 32 times 1/4 is 8. 8 minus 2 is 6. Fractions. What could we do to make all the fractions go away? So, calculus is easy, algebra is hard question here. What do I do to make those fractions go away? What could I multiply by that would cancel all of them? What number is big enough to cancel an 8, a 2, and a 4? 8. 8 would work. So let's multiply everybody by 8, both sides. So K minus 4K minus 2. And then probably the most common mistake is to forget to get the 8 on the other side as well. 6 times 8 is 48. So what is that? Negative 3K equals 50. So K equals negative 50/3. That's a terrible value for K, but we don't mind terrible values, especially if it's the last step of a problem. And it's not an answer choice because we made a mistake. So blah, blah, blah. Negative 50 thirds. Yeah. Calculus is easy, algebra is hard. So hard that whoever wrote the notes couldn't come up with the right solution. Number 6, graphical base. So we like these. Which of the following statements is true? G has an infinite discontinuity at x equals 1. True or false? True. There's an asymptote there. And we don't really care if they're both going up or both going down, or in this case they're split. Like, it doesn't matter. There's an asymptote there. So that is not continuous. In fact, that's a infinite discontinuity. So that is true. Non-removable discontinuity. Okay, so that's a different word. That just means I can't fix it. It's not a hole. A non-removable discontinuity at x equals negative 1. Okay, does that look fixable to you? At negative 1? No, like that's a jump. So that is non-removable. I can't fix that. That's true. It's not fixable. Statement 3. G has a non-removable, not fixable discontinuity at x equals 2. All right, so at x equals 2, would that be an easy fix? Yeah, if you could just fill in the hole, we'd be good. So it's a discontinuity, but it's a removable discontinuity. So 3 is false. So 1 and 2 are true. So be careful. That one tests removable versus not removable. So x equals 2, discontinuity, but it's a hole, it's a fixable one, not a not fixable one. 7, we did all these kind of things already. This is just plugging in 3 at branch A and branch B. So I don't know that we need to do all those. All you do is plug in 3 everywhere and see if they match. And if they match, you're good. And if they don't match, you're not good. Although be careful, jump discontinuity, this last one, first one's continuous, this one's not continuous. But let's look at this last one. It's not continuous with a jump. So F is no, G is yes. Let's look at this last one. So if I plug in 3 to branch A, 2 times 9 minus 5 times 3 plus 2, 18 minus 15 plus 2 is 5. And then if I plug in 3 to branch B, 3 squared minus 6, 9 minus 6 is 3. Those don't match. So this is not continuous. But what kind of not continuous is it? Because branch A branch B is true everywhere except x equals 3. So there's what B looks like. Parabola, but I did that wrong. Did it backwards. Branch A is the parabola. Branch B is the hole, or is the dot. We said that was at 3, so that'd be like down here somewhere. So it's not continuous, but read the question carefully. Does it have a jump discontinuity? It has a discontinuity. Is that a jump discontinuity? It's a hole, not a jump. So that's tricky. So the only one is G. That has a jump discontinuity. So that word jump is important as opposed to a removable point discontinuity. All right, the assignment is worksheet 4, I think. Whatever one's next, I think it's worksheet 4. Again, backing up, big picture. Let's turn all the way back to the front of these notes. Like just looking at a picture, continuity is easy. Yes, continuous. No, no, no. But then we get into the details about point versus asymptote or infinite versus jump. You can fix a hole, you can't fix the other two. So that's what I mean by conceptually, it's easy to look at a picture and know, yeah, I can draw that, or no, I can't. But then the technical stuff gets a little tricky with new words and definitions or with limits. So be careful. You gotta understand both things, the concept, but also the kind of technical nature of it.